Video 4 of Chapter 9, where we are going to discuss two-sided significance or hypothesis tests for proportions. Now, so far we have only really considered alternate hypotheses that are one-sided, meaning we only hypothesized in one direction. We only considered cases where maybe the truth was less than a claimed value, or maybe the truth was greater than a hypothesized value. Now, at the beginning of the chapter, we said there are really three different possibilities for the alternate hypothesis sign. We could use less than, we could use greater than, or we could use not equal to. And it's going to be in this video that we finally get to discuss the not equal to alternate hypothesis scenario. Now, we're going to use that not equal to sign when we don't know which way the alternate value is really going to go. And so therefore we will do a two-sided test. So the population proportion, we don't know if it technically could be smaller or larger than whatever the hypothesized value is. And there's going to be times where maybe we just want to test that it's different from a particular number, but we don't know which way it goes. So the only big difference that a two-sided test has over a one-sided test really relates to the p-value at the end of the problem. Since we initially don't know if we're going to be below or above the hypothesized value, then we're going to need to double our p-value. And that's literally going to be the only big difference here. Now, here's the thing. We cannot take a random sample, look at where that sample statistic is, where that sample proportion is, and see if it's really above or below the hypothesized value, and then decide from there if our alternate hypothesis should be less than or greater than, and make it a one-sided test. You really have to have the idea before you take your random sample and look at your sample proportion to decide if it really should be a one-sided or two-sided test. Now, how are you going to know if a problem's one-sided or two-sided? Well, you got to find and look for those keywords in the problem. So if the problem states that they're looking for, a smaller difference or a greater difference, or that you're looking for an increase in the proportion or a decrease, that's really going to let you know if they're looking for more of a less than or a greater than one-sided situation. But if the problem just states that they're looking for a difference and they're not specifying which direction that difference has to be in, then we're going to have to consider a two-sided test. So here's a visual representation of really that big difference between one-sided and two-sided tests. If our alternate hypothesis involved a less than one-sided test, then our p-value is going to be on the left side of the distribution. Versus if we had a greater than alternate hypothesis, then our p-value ends up being on the right side of our sampling distribution. But for a two-sided test, again, we don't know which side of the sampling distribution we're going to end up on. So if we happen to end up on the left side of the distribution, then we're going to have to double that p-value to give us both tail ends, because again, we technically didn't know which side we would have initially been on. And then there's going to be times where maybe we do a two-sided test and we're going to end up on the right side of the sampling distribution. But again, we didn't know we were going to end up over here, so we'll double that value so that we can symmetrically get this opposite tail end, and that gives us the total p-value. Now, we're going to look at an example involving a coin. And a coin that is balanced should come up heads half of the time in the long run, right? 50% heads, 50% tails. Well, there was this old French guy back in the 1700s named Count Buffon, and he wanted to test whether his coin was truly balanced, aka that it was fair. So nothing else going on in the 1700s in France, so why not toss a coin 4,040 times? And you know what? He got 2,048 heads. Now, is this evidence that Count Buffon's coin was not actually balanced or was not fair? If we consider if he flipped this coin 4,040 times, well, if the coin really is fair and it should come up 50% heads, then half of these 4,040 flips would be 2,020 flips. And so consider what he got. He was 28 more head flips than what he would have expected to happen. So is 28 more heads really a significant difference that we think his coin is not fair? So our hypotheses. We could state this technically in words to say that the null hypothesis is that the coin is balanced, that it's fair. versus the alternate hypothesis is that the coin is unbalanced, or it's not balanced, or it's not fair. Or we're going to write it typically as our symbols with our numbers. So this is the way I would typically write it, but technically if you wanted to write it in words, that scenario would work out. So again, our null hypothesis is that the proportion of our coin flips that end up heads is 50%, which means the tails are also the other 50%, and therefore the coin is fair. Versus, on the other hand, we don't necessarily know that if the coin is not fair, if it is unbalanced, we truly don't know if we're going to see more heads or more tails happen. So the proportion of coin flips that land heads might be greater than 50%, or it might be less than 50%. We don't know which way the balance is off on that coin. Now, for the conditions, I'm just going to kind of gloss through these here, but we're going to assume that the coin flips are truly random. For the independent condition, could he flip the coin more than 40,400 times? Sure. He's a bored French guy. He could certainly do that. For the normal condition, is n times p and n times 1 minus p both greater than or equal to 10? Consider the p, we have to use the hypothesized value of 50%. So really, how many hypothesized successes and how many hypothesized failures would we expect to see out of our 4,040 flips? Well, 2,020 heads and 2,020 tails, both of which are greater than or equal to 10. So therefore, our sampling distribution is approximately normal. So therefore, we will get to use normal CDF later to calculate the p-value. Now, to do the calculations with the formula, and again, I will show you next what it's going to look like to do the calculations with the calculator command. But if you wanted to go this route, you certainly may. So here is our same test statistic formula that we used previously, but for a one-sided test. This is now going to be for a two-sided test. So I have my sample proportion. I have 2,048 heads out of 40 flips, minus my hypothesized value that I should get 50% heads, divided by my full standard error, my big square root down here, and that gives me a standardized test statistic of 0.8810. So one thing to consider before I get to the p-value is, even though he was 28 heads above average, 28 heads above average is not even one standard deviation away from the mean, which really isn't going to give us that small of a p-value. So to calculate the said p-value, what is the probability that we would find other test statistics that are as extreme or more extreme than our positive 0.8810? So using our normal CDF, we're going to start with our 0.8810 and go up to infinity with our typical mean and standard deviation of 0 and 1. And so this would be where we would typically stop in our calculations. We'd say this is our p-value. It's almost 19%. But this is where we have to consider. We have to go back and look at the alternate hypothesis and look and see that it was a two-sided test. This is just one of those things you're going to have to go back and remember. And it's the most common thing that people will forget to do if they do the calculations by hand. So in the end, since this is a two-sided test, I technically need to say, I'm going to multiply this by 2, and I always say times 2 tails because there's 2 tail ends here. This 0.1891 represents one of my tails, but I need a second tail. So the two-sided p-value is approximately 0.782. Now, if I want to do the same thing with my calculator, this is going to be a little bit nicer because the calculator, as long as we tell it it's a two-sided test, then we don't have to worry about doubling the p-value. So this is a one proportion z-test. So I go stat over to test, go down to number 5 for a one prop z-test. My null hypothesis, my claimed proportion is going to be 50%. And then I put in X and N as what I saw in my sample proportion. We saw 2,048 heads out of 4,040 coin flips. And then for the proportion, I'm going to select the first one because I was just saying, I don't know if I'm going to see more or less than 50% of coin flips end up heads. So this one is what makes it a two-sided test. If you select less than or greater than, that's what really makes it a one-sided test. So then I go down, hit calculate, and then here's what I get. It gives me, notice, the same test statistic. And notice this time it went ahead and doubled the p-value for me. So whatever p-value you get when you say it's a two-sided test, it will truly make that a two-sided p-value, and you don't have to worry about doubling it. So again, if you want to use the calculator, remember you're going to have to call this a one sample z-test for p, or for a proportion. You have to tell me the test statistic z, you have to tell me the p-value, and then you can move on. So now we get to our conclusion. We have this p-value, we have the alpha level. The p-value is clearly not less than the alpha level. Even when it was a one-sided test, right? Even when it was a one-sided, we were at like 18, 19%. So we weren't even going to change our mind when we doubled it anyway, right? So p-value is not less than the alpha. So in the end, we will fail to reject the null hypothesis. So in the end, we do not have enough evidence at the alpha equals 0.05 level to conclude, and remember, we're always trying to conclude the alternate hypothesis, and that would be that the proportion of coin flips that land heads is not equal to 50%. Now, if we were to take a look at a 95% confidence interval for this problem, wait a second. Did you just say confidence interval? I thought this whole chapter was about hypothesis testing. Confidence intervals were last chapter, so what on earth are we doing talking about confidence intervals? Well, the thing is, we can actually make a connection between our hypothesis testing and our confidence intervals, but only if we discuss two-sided hypothesis tests. And the main reason why two-sided tests work great with confidence intervals is because confidence intervals are two-sided. We have a lower limit and an upper limit. Now, one-sided hypothesis tests technically, I guess, could be compared to a confidence interval. But if it's one-sided, then it's really like we would only know one side of our confidence interval, and we wouldn't really know where the end of it would be. So in this scenario, I guess we would say the end would be at 100%. Or if we were to look at the other side of a one-sided test, then maybe we know the upper limit is confined to being no more than 0.52235, but then the lower limit we don't really know. So technically you would have to go all the way down to 0. So it's not as helpful as compared to when we have a two-sided hypothesis test with a confidence interval to use. So how does this 95% confidence interval support the conclusion of our significance test that we just finished at an alpha level of 5%? Now, you might be wondering one thing. Is there a special relationship between the confidence level and the significance level here? And there absolutely is. So because we had already established a 5% significance level, then I would have to use a 95% confidence interval to make them fully comparable. So the confidence level and the alpha level have to add up to be 100%. So remember, our null hypothesis was that the proportion of coin flips that land heads would be 50%. So can we reject a 50% claim? And no, the confidence interval is telling us a 50% claim is a plausible population value. So again, we failed to reject with the hypothesis test, we failed to reject that the coin was unbalanced, and the confidence interval is also supporting that same claim, that we would not be able to reject the 50% null hypothesis claim. All right, now we're going to take a look at another example, except this one's going to be a two-sided test that's for two samples. The coin example was a two-sided test for a one-sample problem. We just had the one coin. So this problem says, a recent study of peanut allergies explored whether early exposure to peanuts helps or hurts subsequent development of an allergy to peanuts. Infants who had shown evidence of other kinds of allergies were randomly assigned to one of two treatment groups. One group was given baby food containing peanut butter, while the control group was given baby food that avoided peanut butter. 5 years later, 10 of the 307 children in the first group were found to be allergic to peanut butter, while 55 of the 320 children in the control group were found to be allergic to peanut butter. Does this study provide convincing evidence at the alpha equals 0.01 level that there is a difference in the development of peanut allergies? Now, for the hypotheses, we're initially going to say that the null hypothesis is there's no difference. If you give a baby peanut butter or food with peanut butter versus food without a peanut butter, they're still equally likely to develop allergies to peanuts later in life. But the alternate hypothesis, and this is where initially people are like, why is this two-sided? Shouldn't we show that it's greater than or less than, that one group would be more prone to peanut allergies than the other? And so the thing is, at the initial onset of this study, the researchers didn't know if exposing babies to peanuts early on, if it would help them to kind of reduce the amount of allergies to peanuts, or if it actually would kind of hurt, that it would actually increase the amount of the incidence of kids that are allergic to peanuts. So they had no idea whether this was going to be helpful research kind of in a good way for these babies, or if we're really going to screw up a lot of babies and we're going to have a lot of kids that are allergic to peanuts later in life. So that's why this is a two-sided test. We don't know if we're going to end up helping these kids or really harming these kids more. Now, in terms of the conditions, that one thing, or kind of two things with conditions. The first one is about the random condition. These infants were not randomly chosen to be a part of this medical study. They were randomly assigned, though, to one of the two treatment groups. So since these are volunteers and they're not randomly selected, then we still have to have some sort of randomization happen in this experiment. And so the randomization comes in from the random assignment to the treatments. So for the random condition, you can state they're not randomly selected, but they are randomly assigned to the treatments. That still counts. The other special note about conditions deals with the independent condition. Since the infants were not selected from the population in general, then technically we don't have to check the independent condition. But what if I do check the independent condition? If you do check it, then it's okay. You're not going to be dinged any points on the chapter test or on the AP exam, as long as you check the condition and you don't make any kind of mistakes with it. So in prior years on the AP exam, they have said for problems like this, if a student checks the independent condition, as long as it looks okay, then we're just going to ignore it because they didn't technically have to do it. Now, we're going to jump ahead for the calculations, and I'm going to go ahead and tell you up front that the test statistic is negative 5.707. And so now, what's the p-value from that test statistic? And what's our overall conclusion? So since my test statistic is negative, then I would want to find the probability that other test statistics that are less than or equal to negative 5.707. So I get to use my normal CDF. And again, I just kind of glanced over the normal condition. It met, so I'm allowed to use the normal condition. So negative infinity up to negative 5.707 for my upper bound. Mu and sigma are both my typical 0 and 1. And so I would get from my calculator a very small p-value. So small that my calculator gives it to me in scientific notation. But I gotta remember that this is technically a one-sided p-value. So once I say times 2, if I'm doing this by hand, if I use the calculator command, it's going to automatically give me the two-sided p-value. But if I only do this by hand and use the normal CDF command, I got to double this. But still, even doubling this crazy small number, it's still crazy small, right? This is still going to be clearly less than an alpha level of 1%. So in the end, our p-value is less than our alpha level. So we will very easily this time around reject the null hypothesis. And so in the end, we can conclude that we do have enough evidence at the alpha equals 0.01 level to conclude that there is a difference. Remember, the null hypothesis was saying there's no difference. But the alternate hypothesis is saying there is some sort of difference. But keep in mind, we didn't really know at the beginning of the problem which way the difference was going to lie. In the end, it seems like that exposing babies to peanut butter early in life as a baby, it does tend to help them not develop peanut allergies later in life as toddlers. So for the you-do problem, sticking with this same example here. Here is the 99% confidence interval. And again, you don't have to worry about getting this confidence interval. This would be basically a follow-up question. And so here's the confidence interval. How does this confidence interval support the conclusion of the significance test that we just did at the 1% level? And remember, because the alpha level was set at 1%, then I needed to calculate a 99% confidence interval. Again, those have to always add up to be 100%. So tell me, why does this confidence interval support the decision that we made to reject the null hypothesis here? And we'll talk about that the next day in class.